Hi, Advanced Algebra 2. Welcome to the Concept 29 notes, sequences and series. These notes will be an introduction to this topic. All right, look at this table at the top of your note sheet. So a sequence is an ordered list of numbers. And then here are two specific types of sequences. So a finite sequence is a function that has a limited number of terms, obviously, and whose domain is the finite set 1, 2, 3, etc. to n. The domain numbers are the position numbers of the terms in the sequence. So 1, 2, 3, we would refer those as the first term, the second, the third. An infinite sequence is a function that continues without stopping and whose domain is the set of positive integers. So here's an example, or at least here's this in mathematical general terms. So domain would be the position of each term. So first, second, third, fourth, all the way up to we say the nth term. And then the range, these would be the actual terms of the sequence. And we use the letter, the variable a, to indicate those. So a sub 1, a sub 2, a sub 3, all the way up to a sub n. So here are two examples. Here's a finite sequence example. So we're just given the range or the terms, which is 2, 4, 6, and 8. So notice we have 4 terms, so our n numbers would be first, second, third, and fourth, and this sequence ends. It's finite. Now we have that same sequence, but it is an infinite because we have the ellipse, the 3 dots at the end, which indicates that this pattern would keep going. Now we can indicate a sequence. It can be expressed by an equation or a rule. And for both of the examples that we just looked at, the rule could be given that a sub n, that means any term in the sequence, can be found by taking 2 times n, or 2 times the position number. So see the third number, 3 times 2 is 6. We can also write that in function notation. So f of n, any term in the sequence, would be 2 times the position number. Just know that we start the counting of the terms. The domain will start at 1 unless otherwise indicated. Okay, now this right here is an exploration. So I don't want you to stress over this. Sorry, let me jump back. And I don't want you to stress over these, but just try your hand at looking at these patterns one at a time. See if you can describe the pattern and then write a rule in terms of the position number, in terms of n. So what I usually do is I will write the position numbers either above or below the terms in the sequence. So for A, I'm going to go ahead and write, so I have position numbers 1 through 5, and I just put the n on the end. And then I notice that I start with 1, and then I go to 2.5 and 4. So I notice I'm adding 1.5 each time. So I'm just going to write that description. So I start with 1, and then I add 1.5 each step of the way. Now to write a rule, though, in terms of the position number n, what happens is that from the first to the second term, I add 1.5 once. And then from second to the third term, I add 1.5 twice. So what I'm doing is adding 1.5 times 1 less than the position number. So take a moment and look at that and see if it works. So 1 plus 1.5 to, if I'm going to the second term, times 1 gets me up to the second term. All right, now let's look at B. So we started 8, down to 6.5, down to 5. So now we are decreasing by 1.5 each time. So I'm going to write my position numbers just so I have them in my head. And what I notice is that I decrease my term by 1.5 each time, or 1 less than the position number. So for term number 2, I decrease 8 by 1.5 once. For term number 3, I decrease 8 by 1.5 twice. See how that works? By term number 4, I decrease 8 by 1.5 3 times. So for any term, I'm decreasing 8 by 1.5 times 1 less than the term number, n minus 1. All right, you may be going, what? Okay, so just hang with me. Now look at this pattern. It's different. So I'm going to write the position numbers. Now take a moment, look at the position numbers, and compare them to the terms. So the 4 in the denominator just repeats every time, and that pattern will continue. Notice the numerator looks like it's the position number squared, and that pattern holds for each one that we can see. So let's go ahead and describe that the position number squared divided by 4 will generate a term. So we can say any term a sub n equals n squared over 4. Now D is similar, but it's a little tricky. So let's write the position numbers and then take a moment and see what's happening. So we have 4 repeated in the denominator, and then in our numerator for the first term, that is 5 squared. That's 6 away from 1. Then we have 4 squared for our second term numerator, and that is also 6 away from 2. And then for our third term, we have 3 squared, 9, which is also 6 away from 3, or negative 3 is. So if we take the position number and we subtract 6 and then square that value, that will give us our numerator. And it's that divided by 4. What a crazy pattern. So a sub n equals n minus 6 squared over 4. All right, moving on, let's put in our position numbers. Now it's easy to see what's happening from one term to the next, but think about it in terms of the position number. Also notice that we are doubling each time. So since we are doubling something each time, we can use that number 2. And then if you look at the position numbers compared to the terms in the sequence, you could see that 2 to the negative 1 power is a half, 2 to the 0 power is 2, 2 to the first power is 1. So if you take 2 and raise it to a power that is 2 less than the position number, I know that's confusing. So we could write our rule something like a sub n equals 2 raised to the n minus 2. Yes, a wacky pattern. All right, now look at F. Let's put those position numbers, 1, 2, 3, 4, and 5. And again, think about it in terms of the position numbers. We can see that each time from one term to the next, we are decreasing by a half. But how can we do that in terms of the position number? So if we start with 8, and then we decrease by a half each time. So as a rule, we could write that as a sub n equals 8 times a half, and then to the n minus 1. So for example, our first term, if we take 8 times a half raised to the 1 minus 1, which is 0, that would just be 8 times 1, which is 8. For our second term, if we take 8 times a half raised to the 2 minus 1, or the first power, that would give us 4. All right, just wanted to give you a little exposure with some sequences and figuring out the rules. Do not fret though, as we get into this unit, you will find out specifically, and a process how to figure out what's going on with the sequences and how to write a rule. All right, now let's look at example 1. We're just going to write the terms of the sequence, and we're given the rule for the sequence. So the first 6 terms. So we have the sequence that's given by the rule a sub n equals 2n plus 5. Remember, n is the position number. So we'll just start by plugging in 1. So 2 times 1 plus 5 will give us 7, and then 2, which gives us 4 plus 5, or 9. And you can see the pattern here that we're increasing by 2 each time. A sub 5 is 5 times 2, or 10, plus 5, which is 15. And then finally, a sub 6 is 2 times 6, 12, plus 5, which is 17. Now let's look at B. So this is a little bit different of a pattern. We have negative 3 raised to the n minus 1. So we'll start with our first term, f of 1. So that's negative 3 raised to the 0, which is 1. And then f of 2, negative 3 raised to the first power, which is negative 3. And I'll go back up there and fix that in a moment. Negative 3 squared is 9. F of 4, negative 3 squared to the third power, negative 27. F of 5 is negative 3 raised to the fourth power, which is positive 81. Just notice on that, when we have a base of a negative number raised to a powers that, go up to the first 0 power, the first power, the second power, notice how the negative alternates in our terms. So positive 1, negative 3, positive 9, negative 27. All right, so you write the first 6 terms of the sequence. So plug in 1, a sub 1 would be 1 plus 4 or 5. A sub 2, 2 plus 4 or 6. A sub 3 would be 7. You can see we are increasing by 1, started at 4. And then a sub 6 is 6 plus 4 or 10. On D, we have one of those bases that's a negative, so we're going to see terms where we have alternating negative signs. So negative 2 raised to the 2 minus 1, or first power, is negative 2. Negative 2 raised to the second power, we come positive 4. F of 4 will be negative 8. F of 5 is positive 16. And so because our powers switch from being odd powers, even powers. All right, finally, this is a different kind of pattern. So a sub 1 is 1 over 1 plus 1, which is 2. A sub 2 is 2 over 3. A sub 3 is 3/4. A sub 4 is 4/5. A sub 5 is 5/6. And A sub 6 is 6/7. All right, so that was just to practice writing terms of it. Now let's look at this real life situation. So you work in a grocery store and you're stacking apples in the shape of a square pyramid with 7 layers. So write a rule for the number of layers, apples in each layer. The first layer is the top layer, so is with 1 apple. The second layer has 4 apples, and then the third layer, it would continue in the like manner. You wouldn't build it that way, but that's how we're going to describe it. Now that is a very poor picture of 1 apple with 4 underneath it. So let's make a table, layer compared to apples. So I'm going to give myself enough space for 7 layers. So I know that my first layer has 1 apple, my second layer has 4 apples. So I'm looking at a pattern, and I notice if I take my number of layers and if I square it, then I get my number of apples. So my third layer would be 9, and if I'm picturing that, that would actually work. That would be enough apples to support the layer above it. 4 squared is 16. The 5th layer would have 25 apples. The 6th layer would have 36 apples, and the 7th layer would have 49 apples. Now, what is the rule for this? So if we think of our layer as n, then our apples at any layer would be the layer squared, or a sub n would equal n squared. This concludes the first part of the concept 29 notes. So in part 2, we'll look at summation notation and just an introduction to that.